A very important part of information security is protecting applications. We can use the analogy that an information system is sort of like a house. We have a foundation of policy, we have walls that separate the inside from the outside and also separate different parts within the inside. And those are very much like our network controls at the perimeter and, of course, protecting different parts of the network from another. We have windows that provide a certain level of, shall we say, visibility into our data, but we then limit that through blinds and curtains. That provides cryptography. We have a front door which allows access, but at the same time only allows access to the people with the right key, as in cryptography. The roof of the building is like the application. It is what faces the sun and the rain and the elements. And, as we know, if there's even the smallest hole in the roof, everything below that in the building can be damaged. That is why it's so important that we build a good roof. And in the information systems world, it's the same thing. Applications are like that roof, and the smallest vulnerability in an application may mean that all of the work below that, whether or not we're talking about access control or networks, can be compromised. We know that network security alone cannot adequately protect an application. The controls must be built into the application to protect the application itself from compromise. Certainly, network security is important, but we should not rely on network security to do what application security should be doing. Some of the objectives then for putting in proper application-based controls. To ensure that the application processes a transaction correctly. If you go to an ATM and make a deposit, you want to make sure that that money went into the right account. That is certainly a form of integrity of process. You want to make sure that when you deposit money into your account, it's the exact amount you put in, not more or less $10, $15 here or there. That's the integrity then of the data. We want to ensure that only valid input data is processed, to make sure that a person could not access your account or they could not do some type of invalid transaction. And we want to ensure that the application and of course the data itself is available to those who need it. So what are some of the application controls we use? We use them to protect data, we can say here, to be complete, that a person cannot half fill in a form. And they leave a spot on the form blank, that then of course would error out and tell them you must fill in this field. We have to make sure it's consistent in format, especially something like dates. Are we going to use a date format of year, month, day, year, day, month, year? Yeah, there's many different formats. In order to preserve the integrity and trustworthiness of our data, it must be in a consistent format. It should be accurate, that the information we process, make sure it's correct as much as we possibly can. It also should be valid. A person should not be able to enter in a date of the 31st of June or the 29th of February in most years. It also should be linked to the person who made that change. We can call this accountability or auditability. Here we'll call it verifiability. The ability to verify or validate, tracking and logging of who made this change in case there's some questions about it later or we need to do an investigation. We've often thought that one of the most important application controls is input validation. We've often heard that statement, garbage in equals garbage out. So one of our most important considerations here is controlling that garbage in, trying to ensure that we've put in controls here to try to ensure we don't accept invalid information. This can prevent the contamination of the data within our systems, and in many cases, we take especially with web-based attacks, many of the web-based attacks, cross-site scripting, cross-site request forging, buffer overflows, SQL injection. These all can be prevented, or at least the first line of defense against these many types of attacks is proper input validation. We also want to ensure that only authorized personnel can make changes, can put data in. Nobody else should be able to then change your bank account. Nobody else should be able to make a change to that system if it's not within their job responsibilities. So this is where we put in things such as, read-only instead of a read-write access for a person. The enforcement of concepts such as, least privilege. If you only need to be able to read the data, you won't be able to modify it. We also want to ensure that we have that verifiability. We have a way to associate all input with a person that did provide that input of the data. One of the problems always with a computer system is when we could have duplicate transactions. This also, of course, could lead to the loss of integrity of our data. So this especially happens when we do a transaction to make sure that the transaction completed correctly and that the transaction itself was not a duplicate. Some of the ways we do this is to put in things such as, transaction totals. What was the total value of all the transactions, say for example, in a batch that we processed? We put in checksums or hash values to try to prove, like for example, when you purchase a product, very often you have a product number. That product number actually contains within it a checksum that tries to make sure, we can sometimes call it a check digit, tries to make sure that product number is valid. So if you mistyped it or the person misheard it, it'll come back and say, wait a second, that's not a valid product number because the check digit or checksum associated with it didn't actually agree. We do this one on a file as well. If we have, of course, many different transactions, and you've seen this when you've gone shopping at the store. Quite often at the end of your receipt, it'll show you the total number of transactions or products you purchased, and you can check to see whether or not that total number of products equals the number of products that are shown then on the receipt. These are ways to try to prove integrity, and with batches we'll often do this with having transaction totals, checksums, and hash values to prove that if a transaction, say, or a file has been transmitted, it is still accurate then at the far end. Quite often we'll put in sequence numbers. This is file number 1 or batch number 1, batch number 2. And by putting sequence numbers into header fields and trailers, we can try to make sure that we didn't miss a file, and also try to make sure that we didn't end up processing the same file twice. And putting in total number of items processed can make sure that we didn't end up with just a partial transmission, and that the actual transmission of that file between 2 points did not fail partway through. So what are some of the input controls we use? Quite often we'll put in a reasonableness check. If a transaction is usually going to be between $0 and $50, then we'll automatically query if somebody tries to put in, should we say, 5,000. Then we'll come back and kind of ask, did you mean 50 or did you actually mean 5,000? What's a reasonable value? We put a limit. No, you're not allowed to process more than, quite often with online banking, everybody has a limit of the amount that you're able to actually then process per day. How much can you withdraw from your account in one day? How much can you transfer from one account to another? Those are limit checks. We also put in range checks that are specially used with dates, for example. What are valid dates within the month? And of course, we use things like completeness checks. Have all the fields in this form been filled out? Is there something we missed? Is there, in some cases, yes, a person's put in a zip code, but it's not the right length. Is it complete? We check for duplicates, trying to make sure we don't have two transactions processed the same. Now, this could be not only two transactions processed sequentially, but sometimes we'll put this in place too to make sure A transaction that was processed today doesn't get processed a month later as well. We check for existence. Yes, you must check off to agree to the terms and conditions. If you don't check off that form or that spot in the form, then it'll of course fail because that doesn't exist or that value is not there. We also use this in the database world, where quite often you cannot put in a transaction, say for example with a product number, if that product number does not exist then in the main product database. An important part of applications protection is proper handling of any types of errors. We have to make sure these errors are handled correctly so that they are identified and, of course, allow us to be able to repair or fix that error as well. Now, sometimes we need actually, if the error is within a series of transactions, we might need to reject the entire transaction flow because we would not be able just to isolate one error within a sequence of activities. Or sometimes we can just then reject just the transaction itself that had then that error. With the web, quite often if a person makes a mistake, we might actually stop the session. If we suspect that this could be a person trying to hack or breach our system, and we hit an error, quite often the best thing to do is actually just completely reject and stop or cease that session, forcing the user to log back in again and start from the beginning. It is important that we log all the errors so we can see what types of errors are we having. Now, reviewing the logs can be important for several reasons. One, to see if we are perhaps under some type of a probing attack. But also, logging all of the errors may be able to identify for me cases where we could actually have a problem within the processing where users are hitting similar errors repeatedly, and that could mean that maybe the process itself needs some adjustment. We need to make sure that transactions in our systems process correctly. And this is where we'll put in things like anti-fraud and precautions to try and prevent mistakes. We do this through things like separation of duties. And separation of duties means a person does not control an entire transaction. Instead, we'll break the transaction into individual parts, and different people have to execute different parts. Now, there's several ways of implementing separation of duties, such as mutual exclusivity. We can implement it through then, of course, processes such as then dual control, for example. But separation of duties is very useful in the fact that it can help us then to identify and eliminate mistakes and fraud. The other thing is to provide for proper authorization. And that is, does somebody else have to approve or authorize some type of an input? This also can be a form of certainly separation of duties, as well as it can be just a form of checking and validation. If a person tries to execute a transaction above a certain limit, for example. Today's world is full of online transaction processing. You go, for example, to an ATM or you go to a shop and you make a purchase, that money instantly can be withdrawn or shown as withdrawn from your bank account. When we do that type of online transaction processing, we really need to have controls in place. And these are very often based on what we call the acid test. The acid test stands for, well, atomicity. Atomicity means that the final result of this transaction should be one clear result. If you take $100 out of your bank account, the difference should be that your bank account balance is adjusted by exactly $100 at the conclusion of the transaction. There's no debate about how much should be taken out or what the final value should be. It should result in one atomic value. We also want consistency. The changes that are made are consistent with the rules. And, of course, that if we have several systems involved, Say, for example, you're in an ATM machine. The ATM wants to then give you money out of your account, but the ATM may belong to a different bank than you actually bank with. We want consistency so that the amount of money dispensed is the same amount of money as you asked for. And we want consistency so that the money dispensed by the ATM is the same as the amount that's taken out of your branch. That's what we would call then external consistency. Consistency between two external systems. We also want isolation. Isolation means that if you're at an ATM taking money out of your account, nobody else should be able to access your account at the same time and try to take money out. Because if you had two people trying to do conflicting operations on the same account, it's quite probable that the result would be incorrect in the end. So we lock or we isolate that account while that change is taking place. Once the change has taken place, the money has been given to you, you've taken the money, you've clicked on the button that says, "No thanks, please return my card," then we commit that change. That means that change is now durable, and in database world we say that is a known good point. That means even if there's a failure a few moments later, the database will only roll back to known good points of value. In other words, that change you've made remains permanent. When we talk about database controls, we put in many different types of controls here because databases contain the gold of the kingdom. For many companies today, it's their databases that are really the core of all of their customer and manufacturing operations. We have to make sure that within the database, it's protected from improper alteration and manipulation. It's protected from unauthorized access. We make sure that any changes made with the database are correct. And this is what we'll call then consistency. Make sure that unauthorized people cannot make changes. Make sure that authorized people cannot make improper changes. And to maintain the consistency of all of the related systems when a transaction is then executed. We want to ensure that every record within the database is identifiable by what we'll call a primary key. The primary key then is used as the index most often and is the identifier for that record or for that row. Just as for yourself as an employee. You have an employee ID number, and that employee ID number is a unique identifier for you. Even if there are several people in your company with the same name, you each have a different employee ID number as your primary identifier. In the employee database, your employee ID number is the primary way that we then can look up your information and not the information of others who may have the same name. So when you put that information into the employee database, we actually have to enforce something we call entity integrity. Entity integrity means that that value within that database of the primary key is not duplicated and cannot be null. In other words, there must be a unique value in every primary key. When we link databases together, those linkages must also work. And linkages are usually achieved with databases by taking a primary key from one database and using it as the cross-reference in another database. This allows us to refer from the one database to the other, linking them through those primary keys. Now, the primary key that is implanted into another database is then known as a foreign key. And a referential integrity says that that reference or that link must work. In other words, if I put in a record within a database that says this employee is working on this project, well, the identifier for that project and the identifier for that employee must be valid values. Since they are going to link to other databases, that link must be valid, and therefore we can refer between those two databases that include employee and project information. We also have to ensure that when our application outputs data, that output data is also accurate. And this, of course, means that we deliver correct but also secure data to our users. Obviously, secure display. In some cases, we don't want to show a full credit card number. We'll only show the last 4 digits. We want to ensure that the data which is stored in our systems also is protected, that a person can't get into a database and maybe see credit card data. We put in, of course, things like screen filters, and of course we kind of joke, everybody in the world has the same password, 8 dots. Why? Because whenever a person inputs their password, all we show are dots regardless of what character they put in. We want to make sure that the outputs of our systems are accurate and complete, which is one reason quite often why at the end of a report we'll always put a line that says this is the end of the report. So we know the entire report was printed and we didn't just lose the last page because the printer ran out of paper and we didn't notice. We want to make sure that the output also is complete in the way that we haven't ended up truncating certain values or values that whether fields were not large enough, and so the result was that the data in that field, if we have a field that only had room for 4 digits and all of a sudden we have a 5-digit number, well, it only shows 4 digits in that field. That's incomplete or inaccurate data as well. We put then end of report notices, and of course part of that is even if the report is blank, we'll put in a line that says this report is empty or there is no entries in this report. So we know that that report wasn't just, for example, there wasn't just a mistake, but rather that it truly was empty. We make sure that values are complete and aren't truncated off because the report wasn't large enough to hold those values. And one thing that's important is that we make sure that the output is equal to the input. If I've input 100 transactions, I want to make sure at the end that we still have 100 transactions processed for the value of what the, should we say, checksums and so on were with the original input.